Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Johan Alif Bewan Ajaha and I am 23 years old. Currently, I'm doing my final semester for Bachelor Engineering in Oil and Gas at Faculty of Chemical Engineering located at UiTM Shah Alam. So today, I would like to present my poster for my final year project. For my final year project, I have done a review paper. The title is Smart Nanofiber for Membrane Distillation. So this is the poster for the review paper. And introduce to you my supervisor, which is Dr. Hashima Binti alias. With the rapid growth of nanotechnology, the preparation of electrospoon nanofiber has gained more and more attention owing to their high porosity, strong functional abilities, and high specific surface area. Electrospoon nanofiber membrane is a significant role in various sectors. The electrospoon fiber membrane has overcome the disadvantage of low performance, high energy consumption, and complicated recycling of traditional methods, especially in the field of wastewater treatment such as filtration, chemical precipitation, ion exchange, absorption, and membrane distillation. Membrane distillation is a promising saline water and wastewater treatment technology with high rejection factors that conventional technologies are unable to achieve. Oil spills and industrial wastewater discharge have occurred in a few decades. Water supplies have been severely affected. Water contamination not only contributes to an ecological imbalance but also directly impacts human health. Therefore, the scientists need an urgent solution to develop successful technologies for the purification of wastewater to solve this important problem. Some previously studies reported several methods that have been broadly used in wastewater treatment such as filtration, catalysis, centrifugation, absorption biological treatment, and centrifugation. Too high energy consumption, secondary emission, and unrepeatable use are seen unavoidable. Nevertheless, because of these drawbacks, engineered materials have gained tremendous interest over the past years. For the problem statement, progress on nanofibers development increased rapidly due to their highly porous structure, narrow pore size, and distribution-specific surface area, and compatibility with inorganics. This study will focus on fabrication of nanofibers for membrane distillation application. Various desalination technologies are emerging to tackle the increasing water demand globally. And the objective is to fabricate the nanofiber membrane using electrospinning technique for membrane distillation, to examine the physicochemical properties of fabricated nanofiber membrane, and last, to evaluate the membrane separation performance of the membrane distillation. And now for the overview of membrane distillation. A thermally driven membrane separation process is membrane distillation. Membrane distillation was first patented in 1963. Nevertheless, until the early 1980s, when more powerful module membranes became available, the membrane distillation did not attract significant interest. In membrane distillation process, vapor pressure is produced across the two sides of the hydrophobic porous membrane by circulating the hot feed and cold permeate in a typical membrane distillation. You can see at the figure to help you to understand more about what I am talking about. To produce the distillate, the vapor produced on the hot feed side passes through the membrane and condenses on the cold side. As the temperature difference between the feed and the permeate increase, the vapor pressure difference increase. Membrane distillation, however, is usually considered a low temperature process that operates below 80 Celsius. As you can see on the figure, molecules of water vapor can move through the pores of the membrane in the hot feed, while the liquid feed is unable to transport through the pores of the membrane. This phenomenon is largely due to the membrane distillation hydrophobic nature and its low surface energy. It is necessary to keep the pores of the membrane dry in the membrane distillation process to prevent the liquid feed from passing directly through the hydrophobic membrane. The material membrane must be low surface energy and non-polar. Since water with high surface tension is polar in nature, The low surface energy of the membrane thus prevents the membrane from wetting. And now we move to membrane distillation configuration. Depending on the method in which the permit site is processed, the membrane distillation process is divided into 4 configurations. First is direct contact membrane distillation, which is DCMD. Second, sweeping gas membrane distillation, SGMD. And third, vacuum membrane distillation, which is VMD. And last is distillation of air gap membrane distillation, AGMD. The various MD configuration have been thoroughly explained and reviewed in many articles. The contrast between the membrane distillation you can see on the figure. All configuration has its own benefit and weakness. AGMD is known as having the best energy performance and efficiency. For commercial application, it is more common. The width of the air gap is normally in the 2 to 10 mm range, which is much greater than the thickness of the membrane, which is typically less than 300 nanometer. Due to its higher thermal and mass transfer resistance, the air gap, which is known to be the main controlling factor. A pump is applied in VMD to produce vacuum in the permit part. Thus, a vapor pressure differential is created through the membrane. An external condenser condenses the vapor. There is low conduction heat loss in this setup, making it beneficial for membrane distillation. Generally, due to high pore wetting possibilities, small pore size are used in VMD. VMD is commonly used for the removal of volatile aqueous solution materials. Even so, in SGMD, the gas travels or sweeps and the vapor is concentrated in an external condenser. SGMD is very similar to SGMD. Compared to SGMD, DGMD has lower mass transfer rates and higher loss of conduction heat than SCMD. However, among the 4 types, DCMD is the most studied membrane distillation type, which are more than 50% of all MD studies owing to its simplicity in function and design. Also, DCMD is the lowest energy efficiency of all configurations, mainly because of their heat loss is high from the conduction through the thin membrane. And in conclusion, DCMD is the most suitable membrane type for MD due to their simplicity and lowest energy efficiency. DCMD also can be considered at commercial scale. And we move to the fabrication of electrospoon nanofiber membrane. The method of electrospinning has been the synthesis of nanofiber from the high-level electric field polymer solution at room temperature and atmospheric pressure. There are 2 major configurations of electrospinning device, vertical and horizontal. You can look the schematic at the lowest of the poster. And now we move to the modification of nanofibers in membrane distillation. The single performance nanofiber membrane can no longer match the highly powerful processing requirement as electrospoon nanofiber become more widely used. As a result, more people are paying attention to the technologies used to prepare functional electrospoon nanofiber. Many researchers have used pre-electrospinning and post-electrospinning technologies to modify a variety of useful materials with nanofiber in recent years. Nanofiber modification technology, nanofiber surface modification, and thin film composite nanofiber membrane modification are the 3 kinds of electrospinning nanofiber modification technology. Other membrane technologies such as RO, microfiltration and nanofiltration can be combined with MD as well as typical distillation system and low cost energy source. This hybrid system can provide both system installation and concentrated brine discharge with high quality goods and lower energy usage. In fact, if they can fix other system weakness, MD hybrid system are advantageous. And the table here shows the summarization of some membrane distillation. For membrane, for PTLNFM, pollutants is copper ion. Operating parameters is ultra sensitive K-Monzi sensor on cuprum filtration. And flux is 26.7 lmh. Rejection is 96.11 to 99.24%. And for the membrane PVDF bits, the pollutants is produced clean water, and the operating parameters is coolant temperature of 20 Celsius and 3.5% feed concentration, and the flux is 18.6 lmh, and the rejection almost 100%. And for the membrane PVDF nanofibers, pollutants is produced clean water, and the operating parameters is DCMD using 3.5% natrium NaCl solution as feed, and the flux is 49.3 kg per meter, and the rejection is 91.2%. And for the conclusion, to sum up everything that has been stated so far, the system of membrane distillation has been described in the study. The properties, spinning parameters, and application field of the electrospoon nanofibers have been discussed in this study. The electrospinning process is a fascinating way for micro or nanoporous membrane to be made. Porous structure can be prepared with different polymeric electrospoon nanofiber layer. The porosity of electrospoon nanofiber layers is higher compared with traditional membranes, and the pore distribution is uniform. The highly porous structure increase membrane permeability, while the high surface area makes it easy for membranes to work. Significant progress was found in electrospoon membrane manufacturing for water treatment. Nanofibers have a very large specific surface area and a very high surface area to volume ratio. They may build highly porous mesh network with great interconnectivity between their pores, making them an appealing candidate for a variety of advanced applications. Membrane distillation is one of the most promising fields of application for membrane electrospoon. For further development in medium-term development, the porous structure, hydrophobic, and membrane performance are crucial. This review shows that nanofiber layers could be used in membrane distillation. And for the acknowledgement, the author, which is me, would like to thank the supervisors for the opportunities and their guidance in completing this research. I think that's all from me. Thank you for watching my video.